In this lecture, we study random permutation, also known as random shuffling. Given n cards and a random number generator, we seek to randomly shuffle the n cards. The objective of random permutation is that all the possible orders can happen, and they happen with the same probability. Here is an example. We are given 7 cards. We want to randomly permute them. It's just like the random shuffling when we play poker. We hope that after the shuffling, the order of the cards is purely random. The order before the shuffling and after the shuffling are totally irrelevant. Knowing the original order does not provide any information about the order after shuffling. Before introducing random permutation algorithms, let's formally define uniform random permutation. In this example, the set contains 3 elements, A, B, and C. There are 6 ways of permuting the elements: ABC, ACB, BAC, BCA, CAB, and CBA. More generally speaking, if a set contains n elements, then the number of permutations is the factorial of n. Here is the definition of factorial. The factorial of n is n times n minus 1 times n minus 2 dots 3 times 2 times 1. Look at the example above. The number of elements is n equal to 3. The factorial of 3 is equal to 3 times 2 times 1 is equal to 6. So the number of permutation is 6. What is uniform random permutation? It means uniformly selecting one sequence out of all the possible sequences. The sequences are selected with equal probability. In this example, all the 6 sequences are selected with probability equal to 1/6. If we perform random sampling from the 6 sequences, then the selected sequence is a uniform random permutation. Here is an equivalent definition. An element can appear in any of the n positions. The probabilities are the same. They are all equal to 1 over n. In our example, an element can appear in the first, second, or third position. The probabilities are all 1/3. Let's study element A. In 2 out of the 6 sequences, the element A appears in the first position. It means with probability 1/3, A appears in the first position. Similarly, in the 2 sequences, A appears in the second position. In the 2 sequences, A is in the third position. This means element A can appear in all those 3 positions, and the probabilities are all 1/3. Uniform random permutation can be defined in another equivalent way. That is, a position can be filled with any of the n items, and the probabilities are all 1 over n. In this example, a position can be filled with any of A, B, or C with equal probability. For example, let's study the second position. The position can be filled with any of A, B, or C. 2 out of the 6 sequences have the second position filled with A. 2 sequences have the second position filled with B. 2 sequences have the second position filled with C. Clearly, the second position can be filled with any of A, B, and C, and the probabilities are all 1/3. We have defined uniform random permutation. But how can we randomly permute a given sequence? For example, we are given a sequence that contains 1,000 items, and we want to randomly permute them. This is an important problem. For example, machine learning people need to randomly permute data in order to perform stochastic gradient descent. In this lecture, we focus on the Fisher-Yates shuffle. It can generate uniform random permutation. Fisher-Yates shuffle has two versions. One is the original version, and the other is the modern version. Let's begin with the original version. It's published by Fisher and Yates in 1938, almost a century ago. The original version is very simple. It will help you understand random permutation. However, the original version is inefficient. Later on, I will introduce the modern version. The modern version is much faster than the original version. To perform random permutation, we need a random integer generator. A pseudo-random integer generator is okay. It is easy to implement a pseudo-random integer generator. You can go to Wikipedia for the existing algorithms. The random generator takes an integer n as input. N specifies a range that contains all the integers from 0 to n-1. The generator outputs an element in the range. The element is sampled uniformly at random. Uniform means all the elements have equal probability. Assume we have such a random integer generator. With the generator at hand, we can perform random sampling and thereby random permutation. I use this example to demonstrate the original version of Fisher-Yates. We have a set of 7 cards. They are from 8 to 7. We want to randomly permute the cards so that every card will appear in the 7 positions with equal probability. Now, let's run the algorithm to randomly permute the 7 cards. Let's uniformly sample 1 out of the 7 cards. Each card is sampled with probability 1/7. We happen to get 4. Take the card out of the set and put it in the 0th position. Now 6 cards are remaining. Perform a random sampling. Each card is chosen with probability 1/6. We happen to get card 6. Take the card out of the set and put it in the leftmost empty position. That is the first position. There are 5 cards left. Perform another random sampling. Each card is selected with probability 1/5. We happen to get card 2. Move the card to the leftmost vacant position. That is the second position. Perform another random sampling and get ace. Take ace out of the set and put it in the third position. Another random sampling. We happen to get 7. Move card 7 to the leftmost empty position. That is the fourth position. Now, 2 cards are remaining. Perform another random sampling. Each card is sampled with probability 50%. We happen to get card 5. Move the card to the leftmost empty position. That is the 5th position. Finally, there is only 1 card left. We cannot perform random sampling, so we don't perform random sampling. Directly put the remaining card in the last position. The obtained sequence is a uniform random permutation. The algorithm outputs the sequence. Why is the sequence a uniform random permutation? A card can appear in any of the 7 positions, and the probabilities are equal. It can be mathematically proved. Thus, the algorithm produces a uniform random permutation. Let's implement the original version and then analyze its time complexity. The original version is simple and straightforward, but it is slow. The input is an array filled with n elements. Our objective is to randomly shuffle the elements. To perform random permutation, we need a random number generator. I don't want to elaborate on the details of the generator. Simply suppose we have such a generator. Let uniform be the function name. The input is a positive integer, n. Let k be the output integer. K is uniformly sampled from the integer set between 0 and n-1. The algorithm works in this way. We run the random number generator and get a random integer between 0 and n-1. The integer is the index of the selected element. If we happen to get 2, then the second element, c, is selected. Here we count from 0. Take c out of the array and put it in the 0th position. The second entry is now empty. We need to move the rest elements one step left to fill the hole. Otherwise, if a newly generated random number was 2, then no element could be selected. Move these elements a step left. The hole has been filled. Let's analyze the time complexity. The time complexity of generating a random integer is negligible. It's almost a constant time complexity. However, after the sampling, there is a vacant entry in the original array. We need to move the elements on the right side a step left. On average, we need to move half of the elements in the array. This costs O(n) time on average. The per iteration time complexity is O(n), where n is the remaining number of elements in the array. So the overall time complexity is n plus n-1 dots 3 plus 2 plus 1. It is equal to big O of n squared. The overall time complexity is thereby big O of n squared. That's why I said the original version of Fisher-Yates is slow. Next, let's study the modern version of the Fisher-Yates shuffle. Its time complexity is only big O(n). It's much faster than the original version. The algorithm was published by Durstenfeld in 1964. When he invented the algorithm, Durstenfeld was unaware of the Fisher-Yates shuffle. But the new algorithm is actually equivalent to the Fisher-Yates shuffle. That's why the algorithm is called the modern version of the Fisher-Yates shuffle. I use this example to demonstrate the modern version of Fisher-Yates. The input is such an array. It contains 7 elements, A to G. Our goal is to randomly permute this array. The red numbers are the indices. We count from 0. Now, the 0th iteration begins. Perform a random sampling. We happen to get the second element, C. This is the 0th iteration, so the selected element should be placed in the 0th position. We swap the selected element, C, with the 0th element, A. After the swap, C is in the 0th position. The current element in the 0th position is a random sample. each of the 7 elements could become the 0th element. The chances are all 1 over 7. Fix C as the 0th element. We will not change it. Now the first iteration begins. Randomly select an element out of the remaining 6 elements. I happen to get the 5th element, F. This is the first iteration, so the selected element, F, should be moved to the first position. We swap the selected element, F, with the first element, B. After the swap, F is in the first position. The current element in the first position is the result of a random selection. From now on, we fix the first 2 elements and will not change them. The second iteration begins. Select 1 out of the 5 remaining elements. We happen to get the second element, A. This is the second iteration. The selected element, A, should be placed in the second position. But A is already in the second position. Swapping A with itself is just like no swapping. We did not change the second element. It is still A, but it is equivalent to the outcome of random sampling. Now the third iteration begins. Fix the first 3 elements. Randomly select 1 from the remaining 4 elements. We happen to get the 6th element, G. This is the third iteration, so we want to put the selected element, G, in the third position. We swap G with the third element, D. After the swap, G is in the third position. The current element in the third position is the outcome of a random selection. Now the fourth iteration begins. Fix the first 4 elements. Randomly sample an element from the remaining 3 elements. We happen to get the last element, D. This is the fourth iteration. The selected element, D, should be moved to the 4th position. We swap D with the 4th element, E. After the swap, D is in the 4th position. Now, the element in the 4th position is the result of a random sampling. The 5th iteration begins. Fix the first 5 elements. 2 elements are remaining. Randomly select 1 element out of the 2. We happen to get B. This is the 5th iteration, so the selected element, B, should be moved to the 5th position. But B is already in the 5th position, so we don't need to move B. While we have done nothing to B, B is indeed the outcome of a random sampling. Now, there is only 1 element remaining. We cannot perform random sampling from a set that contains only 1 element. So we simply leave this element alone. To this end, we have finished the algorithm. The outcome of the algorithm is the sequence CFAGDBE. The modern version of Fisher-Yates is actually equivalent to the original version. But the modern version is much faster than the original version, and the modern version does not need extra memory. Here is the implementation using C language. Permute is the name of the function. ARR and N are the inputs of the function. ARR is the array to permute. N is the number of elements in the array. the permutation is performed in place. The function directly operates on the input array without using extra memory. The return type is void. The function does not return anything. It is because the randomly shuffled elements are in the input array. The input array is the outcome of the program. The main body of the function is a for loop. The integer I means the ith iteration. We perform a total of n-1 iterations. Integer I grows from 0 to n-2. In the ith iteration, we randomly select an element and put it in the ith position. Let's look into the for loop. The function uniform is a random number generator. It uniformly samples an integer between 0 and n-I-1. Denote the random integer by k. Let j be I plus k. So j is a random integer between I and n-1. We fix the first I elements and perform random sampling over the remaining elements, which are from I to n-1. J is the index of the selected element. Lastly, we swap the ith and jth elements. Here is the reason for performing the swap. This is the ith iteration. We should move the selected element to the ith position. I'd like to use this example to explain the code. Now it is the ith iteration. We work on the elements from the ith to the end. For example, this is the ith position. We perform random sampling on the segment from the ith position to the end. Denote the outcome of the random sampling by j. In this example, the element in the jth position is f. This is the ith iteration. So we should move the selected element to the ith position. We swap the ith and jth elements. After the ith iteration, the element in the ith position is the randomly selected element, f. Finally, let's analyze the time complexity. In each iteration, we randomly generate an integer, j. Its time complexity is constant, unless n is too big. Then we swap the ith and jth elements. The time complexity of swapping is also constant. In sum, the per iteration time complexity is constant. The total number of iterations is n-1. Thus, the overall time complexity of the modern version is big O of n. Let me summarize this lecture. We have studied the problem of random permutation, and then the Fisher-Yates algorithms. We implemented Fisher-Yates in two different ways, the original version and the modern version. We have defined uniform random permutation. Suppose we are given n items. We want to randomly permute the n items. We have studied three equivalent definitions of random permutation. One definition is selecting one out of all the possible sequences uniformly at random. The number of unique sequences is the factorial of n. This is just the definition of random permutation. We cannot possibly implement it, because the factorial is a huge number. An equivalent definition is that the order of an item after the permutation can be any between 0 and n-1 with equal probability. That is to say, each item can go to any of the n positions with equal probability. For example, item A can go to the 0th position, 1st position, and second position with equal probability. An equivalent definition is that a position after the permutation can be filled with any of the n items with equal probability. For example, after the permutation, the second position can be filled with A, B, or C with equal probability. I have elaborated on the Fisher-Yates shuffle and its two ways of implementation. Here is the basic idea of the Fisher-Yates shuffle. In the ith iteration, we randomly select an item from the remaining items and move the selected item to the ith position. We have studied two versions of the Fisher-Yates shuffle. The original version uses an extra array. The time complexity is big O of n squared. The modern version is a much better implementation. It has only big O of n time complexity. It is an in-place algorithm. In-place means to transform the input array without using extra memory. In sum, the modern version uses less memory and less computation. This is the end of this lecture. Thank you for watching this video. The link to my slides can be found below the video.